Every single metric and every single summary that we come up with has a 95% confidence bound around it.
Hi, I'm Kristy McGrath, Vice President of Sales at BlueConduit. Thank you for joining us for BlueConduit's new series, Expert Insights, New Standards for Water Infrastructure, a series of conversations where we dive deep into the world of data science, predictive modeling, water infrastructure, and more. In each episode, we'll feature in-depth discussions with industry experts, thought leaders, and innovators, offering valuable insights on the challenges, innovations, and best practices that are shaping the future of water infrastructure management. Today's conversation will be focused on how water systems and their engineering partners can use predictive modeling to classify service lines as lead or non-lead. Joining me for today's conversation is BlueConduit's Vice President of Data Science, Alice Berners-Lee. In addition to her work at BlueConduit, where she leads the data science team, Alice has over a decade of experience writing custom code to analyze large and complex data sets, completing her PhD work at Johns Hopkins University and postdoctoral work at UC Berkeley and Harvard University. Welcome, Alice.
Hi, thank you for having me.
Absolutely. So, I think let's maybe start from the beginning. We talk a lot about unknown management for lead. So, I think some people might not even necessarily know what that is. So can you talk to me a little bit about what unknown management for lead really is?
Yeah, absolutely. So our customers usually come to us, or at this point in the process, they have an inventory of their service line materials that includes information of different levels of confidence. So oftentimes they've done field inspections, verifications where they have a high confidence that those service lines have a certain material. But they also have information of other levels of confidence. So tap cards, work orders, historical records, and the confidence levels for these sources often differ. They're specific to each system. But then finally, there's service lines where they're completely unknown. So service lines without any past or present material information. And so when we look at an inventory, we use those high confidence material labels to build a model to predict on every single address, including the unknowns. And so this prediction is the form of a probability, or like the likelihood that the line is lead. And it's somewhere between 0 and 100%. And this probability lets us classify unknowns that have high probabilities into lead and ones that have low probabilities into non-lead. And so this is what, those unknowns, the management of them is basically classifying the ones that can be classified into lead or non-lead.
Okay, that makes sense. So I would assume that the ability to actually reclassify your unknown materials from a policy perspective might vary state to state, right? So from a regulation perspective, or how we think about taking that into account when we're providing guidance, can you talk a little bit about that?
Yeah, so when we start reclassifying, this is an early fork in the road. So there are a few states, I'm thinking of Massachusetts, North Carolina, who set their own thresholds of what probabilities will classify into unknowns, lead and non-lead. For instance, North Carolina, anything below 10% likelihood is classified as non-lead, and everything above 80% likelihood is classified as lead. Everything in the middle is some sort of unknown. But for the majority of states, their guidance often states that they want the thresholds to be determined in a way that is statistically and scientifically sound.
Okay, so sounds simple, but I guess we know it isn't. It's why we have a team of data scientists to support this effort. So let's maybe break it down a little bit further. When a customer gets a lead likelihood prediction for a service line, let's say it's a 90% likelihood of lead, what does that mean exactly?
Right. Yeah, so it means that the line itself has a 90% probability of being lead, but it's often hard to think about this on an individual pipe basis because we know that a service line is either lead or it isn't lead. So a good way to understand this is that if you were to inspect that line, but also inspect maybe 9 other lines along with it that all have a 90% likelihood of being lead, you would expect that 9 out of 10 of those lines would be lead, and that one line would be non-lead. And when models behave like this means that they're well calibrated. So the probabilities mean what they sound like they mean. And this is true on the other end of the spectrum as well. So if you inspect 10 lines that have a 20% likelihood of being lead, then you'd expect 2 of them to come up lead, and those remaining 8 to come up as non-lead.
Okay. So it's not necessarily as simple as saying this service line has a 90% likelihood of lead, therefore it must be lead, right? Okay. So, I think as we're supporting customers with making decisions with this data, there's a lot of different things to consider. And actually, I'm thinking I have a visual to pull up that I think kind of when you're talking about numbers, sometimes it's hard to visualize without seeing it. So I'm going to just pull up an example graph here, and then maybe we can talk through this. So in this example, we're looking at a graph of predictive modeling results for an example water system. And when we're thinking about setting thresholds, so drawing that line in the sand, what we're seeing here in this example is on the far left side, that first tall blue bar in the graph is the number of locations within the water system where the likelihood of lead is 10% or less. And then it goes up on the chart here. So we can make a justification for this example that that green line that's drawn there would justify making a decision that says anything less than a 20% likelihood of lead, we'll reclassify those as non-lead. And on the high end of the spectrum, on the right-hand side in this example, anything higher than the 70% likelihood of lead, we'll call that lead. And then again, in the middle, maybe it requires some additional investigation. So I think this is a visual of something similar that you were explaining with North Carolina. However, in states where they've left it up to water systems to make their own or decide on their own thresholds, this is an example of what that could look like.
Yeah, absolutely.
Okay, so how then do you help water systems understand kind of how to digest these results for their system and what to do with a prediction once they've got it?
Yeah, absolutely. And looking at this distribution of probabilities across that probability space is definitely one of the things that we talk about with when we talk to customers, and is one of many things that guide our decision making. But another big, chunk of that we think about when we're thinking about thresholds and having this decision-making process with customers is metrics. And so when we talk about metrics, there's a lot to talk about. People are really familiar with some metrics. So for example, accuracy, the total number that's correct over the total number that you predicted. But we know that using this number is not always a good way to evaluate models, and especially not alone. So for instance, in situations when there's a large class imbalance, which happens a lot with lead service lines, this can lead you astray. So for instance, if you can imagine a system that has 100 service lines and only 15 of them are lead, if you came up with a model that said that 0 are lead, then you would have 85% accuracy, which is pretty good, but you've actually not found any lead and not added any value. So there's other metrics that people may actually be familiar with in other contexts of their lives, like in health and medicine. So for instance, the positive predictive value, if you've ever had like a screening test done and the doctor has said you're at a high risk for a certain issue, they likely also told you the positive predictive value, which estimates out of all the people that have this high risk result on the test, how many of them actually turn out to have the issue that you're screening for. So this is a really important metric within healthcare, and it's a metric that we use also with lead service lines. So the positive predictive value in our context is of the lines that we predict are lead, how many of them actually turn up to be lead. And this metric is also known as precision, and it's one of the many metrics that we talk to customers about when we're setting a threshold to separate those unknowns to that higher lead threshold. But the other end of the spectrum is really what gets talked about the most for compliance. When working with us, customers often have many unknown lines that have a very low probability of being lead. So, that example that you showed sort of goes with that trend. And we can help classify these lines to be non-lead in inventory. So in general, when we talk with customers about the metrics associated with thresholds, we want to ground things in what customers may be interested in or worried about. For instance, when drawing a threshold and saying everything below this is non-lead, how many lines would you expect to actually end up being lead instead? This is the false emission rate. We want that to be low. But another thing we may care about is how many of the true non-leads in the inventory in the ground are classified as such. And this is the true negative rate or specificity. And we want this to be high. But as you increase the threshold of the non-lead, between non-lead and unknown, the true negative rate goes up, but so does the false emission rate that we want to keep down. And these estimates are going to be different for every model. Better models based on better data will have better, easier decisions to make. But there's always going to be trade-offs and, specific things for each system. So because of that, we come into these conversations with a range of recommendations, thresholds that we know that we'll be able to defend given this particular model, and then have a conversation within those recommendations about where those thresholds exactly should be drawn. So we look at how these metrics change with different thresholds and discuss with customers, which types of errors they're the most worried about, and aim to reduce those, and also, what their goals are in classification and aim to hit those.
Okay, great. So it's definitely something where it's never a one size fits all conversation. We're really tailoring these conversations for each water system, their model results, their state guidance, and things like that. So I'm hearing you talk about these metrics. We're not data scientists, but can you explain a little bit about how you compute them?
Yeah, absolutely. Great question. So what we want to estimate with these metrics is, given the model being trained on the data that we have, that the water system has, how will it perform when it's then predicting on these unseen pipes in the ground? But by definition, we don't have access to those pipes that are in the ground. So instead, we use a procedure called bootstrapping, where we force the model to predict on data that the model hasn't seen, but that we do know the material for, so then we can compute these metrics. And I think this is something that definitely is easier to understand when looking at some visuals. So for instance, if we divide the data into a training set here in orange and a test set here in blue of the service lines. So service lines are randomly assigned to these different groups. Then we'll train the model on the training set. So that's the only thing that the model has any knowledge about. And then we see how the model performs when it's predicting on those service lines that are in the test set, and when we're using a certain threshold to decide what lead is. Say here our threshold is 50%. And let's say for this example that we are calculating the recall metric. So this is the number of true lead lines in the ground that the model is accurately classifying as lead using this 50% threshold. And so for this example, it looks like the model with this threshold is at about 75% recall, where 75% of the true lead lines were identified as lead. We'll plot that number here. But this is just one random sample of the data that was held out. So what if there was something, particularly easy or especially difficult about predicting those service lines? We need to collect more examples to get a robust understanding of how the model may perform. So let's do this again. We'll have a different random sample still here in orange and a different test sample. And again, we'll calculate that recall score with the same threshold. And here we see that it does a little better, so closer to 95% recall. And we repeat this procedure hundreds of times until we have an entire distribution of this estimated metric, in this case, recall, with this certain threshold. And this gives us a really robust estimate of what we expect the recall can be. So in this case, it's on average closer to 80%. And we perform this procedure with all of the metrics that we talked about and more. And these help us guide our decision making.
Okay, so the bootstrapping is almost a virtual simulation then, without having to go and actually dig up and put eyes on every single pipe that we're predicting. We can come up with these metrics by doing this virtual simulation of looking at the pipes.
Absolutely, yeah.
Makes sense. Okay, so one other thing I think would be helpful for us to kind of dive into a little bit is the topic of confidence intervals comes up a lot. And we hear people say it's water systems, state regulators, we need to have 95% confidence, for example, in something. So maybe let's dive into a little bit, if you can explain what is the difference between a prediction threshold that we're talking about and a confidence interval, and how they're different.
Yeah, absolutely. Yeah, we hear that a lot. A lot of people really want to know, does this model have 95% confidence? And unfortunately, it's, a lot more complicated than just a yes or no question. Just like how we talked about how accuracy can sometimes be misleading, and you never want to have that be the only metric that you're looking at to describe a model. You really can't find one single calculation that's going to state the totality of the model and say that this model has 95% confidence. Instead, every single metric and every single summary that we come up with has a 95% confidence bounds around it. So let's actually go back to that example of the recall that we were estimating. So if we go back to this example, you can see that there's this distribution and it has a mean that's around, 0.8, maybe 0.78, but it has an entire distribution around that. And what we can do is draw confidence intervals around that where 95% of those bootstrapped examples fall into those lines. And so that's what these red dotted lines are here. It's showing that 95% of the experiments that we ran fell in between these bounds. And so what you can say, given this data, is that we are 95% confident that you would expect to see a recall value no less than 58% and no more than, say, 96%. And so depending on the data, these distributions can look wider or narrower. And so, for instance, this yellow wider distribution here we can say with 95% confidence that this data has a recall of maybe 62%. But for this narrower distribution here in green, we can say with 95% confidence that the recall is no less than 70%. So these two distributions of recall, they're the same average, they're the same summary recall metric, but they have different variances that mean that you can state different things with 95% confidence. And so we calculate these 95% confidence intervals around all of the metrics that we've talked about. We calculate it around the estimated total number of service lines in an inventory, and even around individual service line predictions. So a line with a probability of 90% likelihood of being led, like we talked about earlier, we can see what the confidence intervals around that are and say, maybe for one, it's between 89 and 91% likelihood of being led.
Okay, so like you said, then we can calculate 95% confidence, but depending on the system's modeling results, the interval window might be narrower, it might be wider, depending on what we're actually 95% confident in.
Exactly. And when we summarize these results, when we're sort of in a position where we want to defend these thresholds, whether it's to regulators or to the community, it's worth describing each of these metrics, describing the confidence that we have in each one, and really having this be a fuller picture of how the model is performing, alongside things like we talked about earlier, like the calibration that we expect it to have. And that distribution of probabilities that we looked at earlier. So all of these things go into describing a model and into communicating how confident one should feel when using the model in the field.
Okay. And that makes sense. I mean, I think, understanding that decision making for the water systems that we're working with, they obviously have a lot of things to think about when it comes to risk and public health, and we can understand that they want to feel confident about any decision that they're making using this data. And it's great to hear that we take all of these different things into consideration to really help guide a water system through understanding somewhat complex metrics to be able to make these decisions. And I think what's really important here with this conversation is for everyone to maybe remember that no method is going to be 100% perfect, with the exception of digging every single pipe up and putting eyes on every single pipe. No method of classification is going to be 100% perfect. So where there's true value, I think, in using predictive modeling is that, compared to just using historical records, for example, that we can really quantify the probability, the risk, the confidence down to 0.1%, where in comparison, just using the historic record example, there's not really any way for water systems to know how accurate their historic records are when guiding their decision making. We actually find that oftentimes historic records can be grossly inaccurate. So if you're using inaccurate records to drive your decision making and replacement strategy and things like that, it can really cause you to spend a lot of more time and money and resources to remediate lead, or to prove that you don't have lead, which is an even bigger cost to prove that you don't have lead. So I think that's something important to keep front of mind as well. So I guess, what else, if anything, would you want water systems and engineering partners to know about engaging with predictions to really guide replacement planning decisions or inventory classifications?
Yeah, that's a great question. Actually, even before I answer that, I also sort of want to go back to something that you said. This same procedure that we're using when we are comparing models, when we're comparing thresholds, another thing that we do tend to do because of what you were just saying is we compare our machine learning models to baseline models that have, heuristics that one might use instead of a model, and even compare to just using historical records or something like that. And we do this when we're building models, but we can also use this bootstrapping method and other types of methods that look at sampling non-randomly to try to drill down at certain questions about how the model will or won't generalize across different features of a population. We can, not only say this is how we'd expect these thresholds with this model to perform in the field, but also this is how much better this will do than using a simple heuristic like older homes tend to have lead, or depending only on historical records and not bringing other information in. So this really unlocks a lot of knowledge that you can gain about how you'd expect, depending on different heuristics or models, would affect your decision making using different thresholds and classification. So it really, it helps us with that as well. To go back to your original question about, what I'd like people to know, I think that I would love water systems and engineering firms to know that it's always worth bringing up any concerns or goals that they have around this process. This is a conversation that we have. And we know, like you were saying, that these are really important decisions that have to be made, and they're being made in a lot of uncertainty. And so we want to find thresholds that reflect, the interests of the community, the interests of different, interested groups, really come together to make these decisions. And you might not feel like it's worth bringing up like a certain fear, but oftentimes customers bring up a concern, and we hear, a metric that we can calculate and prioritize. So for instance, a system may say, we're really worried about sending out these mailers that say that your line might be lead, and then have a large proportion of those end up being non-lead, and then we've worried people for no reason. So you voice that concern, and what we hear is, we want to make sure that the false discovery rate is really low, and then we can prioritize that. So we really enjoy these conversations with customers, and we encourage them to communicate any goal, any worry, even if it seems specific or unrelated. We want to hear it.
That's really great. And it's good to hear that we're, really taking the time to make sure that, each of our customers their voice is heard, and we're helping them really through this process. And we're not just, I think that there's a lot of fear around, AI, machine learning, that it's this black box. And I think this process and what you've just described through these conversations hopefully really helps put our customers at ease that, we are real data scientists in the loop, helping them understand this process and make decisions with the results. So that's really, really great to hear. So, I think with that, we can maybe wrap up today's conversation, but thank you so much, Alice, for joining us, and to anyone watching, thank you for joining us for BlueConduit's new series, Expert Insights, New Standards for Water Infrastructure. At BlueConduit, we've really spent nearly a decade now learning from water system experts and building the best predictive modeling tools available to help water systems make high quality and data-driven decisions. If you would like to learn more from our experts, please subscribe to this channel. Check out our blog at BlueConduit.com. There will be more of these interviews coming soon. And if you'd like to learn more about using predictive modeling to reduce unknowns for your system and your inventory, please feel free to reach out to our sales team. We would love to have a conversation with you. Thanks so much. Have a great day.
Thanks for having me.
Thanks. Bye-bye.